Greetings. My name is Oleg Daugovish. I'm a farm advisor with the University of California Cooperative Extension. I do research in vegetable crops and berries. And today I'm going to talk about mostly strawberries, one of our key commodities. With that, I'll go ahead and share my slides. We live here in the coastal California, which is a very desirable place. And as you see on this image, we have a lot of people who like the ocean, which is on your left. There's a boats parked in there and the keys. And the mountains and the foothills are a very desirable place to live as well. And right in the middle here, we're squeezed with production of high value commodities such as strawberries. You can imagine the land is very expensive here and it's difficult to farm. But it's still one of the best places in the world to grow strawberries. And we produce about 90% of North American strawberries in California, valued about $3.5 billion every year. And because it's such a valuable land, we fumigate to control pathogens and pests and weed seed, which is an expensive enterprise. It costs about $12,000 plus per hectare to fumigate soil before you plant strawberry. It's a very rapid system. We'll plant for about 9 months, grow the crop, and then disc the field and prepare it again, fumigate and go again, even though it's a perennial crop. There's very little long-term investment in this production system because the leases, the use of those fields are usually about 3 to 5 years. So it's hard to ensure the stewardship of the long-term issues in such system. As you imagine, we have a lot of regulatory pressure on fumigants and the production of such a valuable crop. And so departments of pesticide regulations trying to phase out fumigants and high-risk pesticides by the year 2050. So we're in a little bit of a difficult situation here. And people ask me, why do you fumigate? What's the reason? It's so expensive. And I show them this slide where the first bed on your front ground has been fumigated, but the rest of the field was not. And it collapsed to this soil-borne pathogen, vascular pathogen, as you see on the right. It's a fungus that enters the vascular system of the plant and stops the flow of water and nutrients, and the plants wilt and die. It's Fusarium oxysporum, Forma specialis fragaria. It's a strawberry fusarium wilt, which is really devastating for us. The same goes for another field. This is a charcoal rot pathogen, Macrophomina phaseolina. And we have a lot of fields like this that do suffer. Even with fumigation, we have losses. And we have continuous issues with those things. And some haven't been documented yet. Obviously, the first line of defense against these pathogens is developing resistance in cultivars. It's not always easy. For example, for charcoal rot, for Macrophomina, every bar here is an entry in infested field that's either a cultivar or a line or somewhere along the genetic selection process. And majority of what we have here in this chart against the plant mortality, the y-axis doesn't look very good. We have a very high mortality in just about everything. The common releases of UC, University of California, Davis breeding program, Warrior and Victor, they still score pretty high on mortality chart here, not quite acceptable for our needs. So it's not an easy pathogen to develop resistance to. And of course, resistance doesn't control the pathogen in soil. We know that, for example, Fusarium multiplies in the roots of resistant varieties too, and other crops as well. So it stays in the soil, even though might not have symptoms of it. And new races emerge all the time too. We have excellent resistance to Fusarium, wilt race 1, but we recently have a new race, race 2, that breaks resistance, and the current resistant cultivars succumb and collapse when this race is present in the soil. We also often have multiple pathogens, so you have to have resistance to multiple pathogens. It's very hard to stack resistance and make this cultivar deliver the quality strawberries with all the traits that it has to have as well. And we have to deal with weeds and other pests, such as insect pests as well. One of the key weeds we struggle, which is among the world's top 10 worst weeds. Many of you know it's the Cyperus esculentus, yellow nutsedge, we call it. It grows right through plastic in those plastic culture strawberry beds. When you have clear mulch, it grows under plastic, and expenses for dealing with this weed are quite dramatic, as you will see it completely outcompetes strawberry and takes over. Anaerobic soil disinfestation, or ASD, as we call it, is a technology that's been developed in Netherlands and in Japan. And we adopted this here and tried to work it for our strawberries about 15 years ago. What it does, it has basically 3 steps. One is we provide an easily digestible carbon source for the microbes. This is a rice bran. We have a rice industry that provides a byproduct. So we use this rice bran to the soil surface. It's get mixed in the soil, covered with impermeable to oxygen tarp that encapsulates the system. And then we also irrigate, not flooding, we irrigate to the full capacity to make sure there's no air pockets left in the system. So I explain it to my growers or clientele that it's kind of like feeding a cow. You have a lining of the cow's stomach being a plastic, in this case, all the microbes under it, just like in the cow's stomach, digest the easily degradable carbon source and provide, and it's pretty toxic, they provide an environment where pathogens and pests are suppressed or killed. So with those 3 inputs, temperature, water, and carbon source being essential components of a ASD triangle, anaerobic conditions themselves are quite important for this, as well as what they generate, such as organic acids, a reduction of iron and manganese ions, volatile compounds that could be toxic to pathogens and germinating weeds and nematodes. And so all those things kind of work together in aggregate, providing the system that changes the microbiology and physics and chemistry of the soil for a period of about 3 to 4 weeks, which is what we do to prepare for strawberry season. If you have interest in this technology and you'd like to learn more and you're not familiar with this, we recently put out a review paper in Advances in Agronomy, and I can give you the link here. It's been around for a while. It's been used in multiple countries for many commodities, vegetables, berries, and other crops with variable degree of success. And this may be a poster picture of this technology in California, one of the early projects we had showing both improvement in strawberry health, productivity, and also weed control when they're grown in a clear mulch compared to the untreated check on the right. And technology has been used by organic, primarily growers in California on over 1,000 acres. It's about 400 hectares or so. And the main complaint is that it's becoming expensive. The cost, it's a factor that circle out in this table, is what growers are primarily interested in. And the main component of it, rice bran, became more and more expensive with more and more use. Plus, we have to share it with the dairy industry and cattle industry that uses it as feed. Plus, the transportation costs for it went up. It's a different location in California. It's Central Valley, about 600 kilometers away from the coast where we grow strawberries. So the rice byproduct has to travel with a high transportation cost to our use sites in coastal California. So over the years, we looked at what can we use for the successful, less expensive ASD as a carbon source. And we looked at coffee grounds and distillers grain from the breweries, grape pomace. Turns out it was to have too much carbon to nitrogen. We have to have this optimal ratio about 15 to 20 to 1. Some things were quite good, but difficult to store, such as grass clippings from our sod operations. We grow quite a bit of sod here on the coast too. We tried liquid products, ethanol, molasses, and glycerin. They seemed to be too expensive for us, or didn't just pencil out to be applied through drip in those bed production systems. So we looked, and the wheat middlings is probably one of the best things we can use today. It's a byproduct of milling industry, and it's much closer to us, to our use sites, compared to the Central California, where the rice bran is produced. So it is cheaper, it's effective, and can be used today in organic fields. But as we look forward, we wanted to see, what do we have a lot of here on the coast? A lot of people, and they produce a lot of waste, food waste predominantly. And in the state of California, there's a bill that requires people to deal with about 20 to 25 million tons of food waste. In United States and California included, we do waste quite a bit. And we don't have enough composting facilities to take care of this problem. And composting takes time. It's expensive too. It takes space. There's smells, flies, rats, all these factors you need to take care of to make sure composting is happening properly. So some municipalities start to install dehydrators or fermenters, they call them. And what they do is they take your food waste. You could put sandwich leftovers and compostable plates, eggshells, and all kind of materials in these machines. And within a matter of 1 or 2 days, they basically separate about 75% of liquids and water, either through evaporation or drainage. And through this time of the process of pre-fermentation, they deliver this product. It looks like soil or peat moss. And we liked it because, first of all, this product doesn't break down in storage. It stays. It doesn't get moldy or attract any pathogens. It's easy to work with. It transports well, mixes with soil really well, has no smell or food safety concerns because we've been pasteurized. One thing we're worried about is presence of salt in our food remains. We all like salty food. Strawberries, it can't tolerate a lot of sodium and chloride in their root zone, so you have to be very careful with application rates, not to become phytotoxic. Another question came around is, well, you eat in different places, in a fancy restaurant, in a cafeteria, at home. If you look at food bank versus fancy restaurant, you might have a different type of leftover. How to ensure consistency? Well, it turns out when it's processed, all the different types of operations, the carbon nitrogen ratio remains about the same, or very similar. So it looks like we're in a good place. Like at least a couple of companies, actually 3 or 4 now, they're trying to market those machines and install them to places where we produce a lot of food waste in coastal California. In British Columbia, in Canada, they actually gave small machines, individual machines for either families or combination of families, so the neighbors could come and dump their food scraps in the evening and see what your neighbors ate for dinner and contribute to the environment in that manner. What I wanted to know first is how good of anaerobic conditions we can get using food waste, or we'll call them DOR, Dehydrated Organic Remnants, DOR. How well do they compare to rice bran, which is our old standard? And in this line here, in this chart, it says separates aerobic and anaerobic conditions, showed us that we're below this line with both ASD rice and ASD-DOR. Looks like it's doing the right thing for us. We start doing field scale projects in a small plot operation. So this is a 7 tons per acre before incorporating the DOR into the soil versus untreated check, which we did fertilize with ammonium sulfate just to mitigate that nitrogen effect we expect by using food dehydrate, which do bring nitrogen, phosphorus, potassium, micronutrients to the soil as well. So when we do this kind of projects, we test the soil for presence of pathogens, but we also add this nice permeable bags that contain, in this case, tubers of Cyperus esculentus, nutsedge, and infested sand. As of a kind of inoculum, we're going to extract from the beds later and analyze. Well, turns out that in the system, about 70% of microsclerotia was reduced, or chocolate pathogen was reduced by using ASD-DOR compared to untreated check, which is on the right side of this divide. And you see that about almost 70% of nutsedge tubers failed to germinate, which is a great news. We have larger plants. They responded to this nitrogen that we provided, and we were worried about chloride and sodium. But at this rate, we have about 133 ppm of chloride, which is just above acceptable of 100. And now sodium is in a reasonable place. We'd like to be less than 300. And also because we mix this product into soil, the porosity and bulk density of soil changes. And it actually was classified as silt loam as opposed to heavier clay loam without incorporation of DOR. Here's some nutsedge tubers. They try to germinate and grow in the ASD-DOR system, but fail to produce viable roots and shoots. And importantly, we have improvements in yield with ASD-DOR, which we didn't expect initially because soil wasn't heavily infested, but we did have them, which is so obviously a big plus for the growers. And there was also less mortality compared to untreated check because of the pathogen presence. As you see on the right, plants are collapsing at a lower rate on the left in ASD-DOR in June, end of the production season. Now you can also see that it happens towards the end of the season, but for the whole season from May till June, mortality was definitely lower with this ASD-DOR treatment system compared to check, untreated check. So we want to get more research done, get multiple seasons of data, and make this material available to organic growers. So we continued working on the small plot scale studies. And here's how 7/10 per acre of material looks like before it mixes into soil. It'll be covered with plastic. Drip irrigation will provide water to saturate the soil. And we have sensors measuring moisture, anaerobic conditions, and temperature as well. On these charts, we have like a cumulative anaerobic hours. The strength and duration add up, and we accumulate those hours of anaerobic conditions. And on this chart, over time, we'd like to overcome this line of 50,000, which is the threshold at which we kill Verticillium dilae, Verticillium wilt pathogen. So we definitely overcame this with this orange line, which is ASD-DOR, and replicates 1 through 3. One replicate had holes. We had tears in plastic, which aerated the system and was discarded. So the first 3 replicates did excellent job, and untreated check, accumulating almost basically 0 hours. So we're doing really well. We know we're getting to the level of conditions that should be suppressive to pathogens. And here we see that we also have, as expected, nitrogen with ASD-DOR as a pre-plant fertilizer for our strawberry. Our chloride is about the same as in previous here, and slight increase in EC, which is electrical conductivity, a measure of salt in the soil. This is nutsedge, yellow nutsedge, germinating uninhibited in the check already, and it looks very well suppressed on the right with ASD-DOR. And most importantly for the growers, the plants grew a lot better. They grew faster. They were 50% larger in February. And the first 8 harvests early season, when strawberries are the most expensive, are about double in yield. This is so it's a huge improvement in production, but also in production when the strawberries are most valuable. A big positive for the growers. This is how the plants looked in February. Low productivity in ASD-DOR compared to very low still in untreated check. And by April, we have first mortality due to pathogens. As you see on the right, we're still holding on here with ASD-DOR. And we looked at Macrophomina phaseolina chocolate rot pathogen. It was reduced to about 70% this year as well. So that being said, interesting technology. We like to use more of it. It's one of the many tools. I remind you, we have to use integrated pest management for those kind of long-term strategies, and incorporate variety resistance, crop rotation if we can, ASD with different components into the decision support matrix or tool that will help our growers and decide how to grow strawberries in this heavily pressurized environment that we have. With this, I'd like to stop and appreciate your attention to this topic. I'll stop sharing and appreciate any comments and questions for that presentation.